So I'm going to talk to you about cross-site request forgery attacks today, mostly about the CSRFGuard project. But since I know for a fact that there are a lot of people who have trouble understanding all the corner cases and all the scenarios that CSRF attack might require, I'm going to start with the basics. So what is actually cross-site request forgery? It has multiple names like CSRF, XSRF, session riding, and confused deputy problem. It is a type of attack where a user is tricked into unknowingly submit a malicious request on a website where he has privileged access to. And the requests are, it's really important, are made blindly on behalf of the victim, inheriting its identity and privileges. This is basically possible because the browser automatically sends existing cookies, basic authentication headers, client certificates within the same domain or subdomains. If a cookie is actually set to a top-level domain, then it will be shared with all its subdomains, but it's important that it does not work the other way around. There's another subset of CSRF attacks, which is called login CSRF, where an attacker actually tricking a user into logging in to a website using a predefined set of credentials so that later on an attacker could review the activity log on his machine. So a little bit of history. Actually started, the first attacks were identified in 2001, but the major or more famous ones were started between 2006 and actually towards 2013. And one of the most famous attacks, and actually the one that kind of was modeled in a lot of CSRF examples, was the ING direct attack, where an attacker could possibly transfer money and steal money from their victims. That was using Firefox 2.0 and Internet Explorer 7. But also lately, even in 2017, there was a router DNS change campaign, or actually a lot of them, or sub-campaigns. So it might be still relevant in some cases. In 2020, CSR vulnerability costed around $5,000 on bounty platforms, but nowadays, in many of the cases, people consider the severity rather low. So the classic example, how would an attack would happen actually? First of all, a simple user, whoever, a victim, would log into his banking account in the browser, and he would leave his maybe tab open. He would, it's not even necessarily mandatory, but so to say, in the meantime, he would probably receive a mail from an attacker who crafted a URL, or maybe just a simple image tag sent through the email. And when the victim would click on it, it would create a request with the credentials already stored, the session cookies of the banking website. And this way, since the browser would not be able to differentiate whether the request was coming from a legitimate user or not, the transfer would happen. This is, of course, not possible lately at all. So maybe another more recent example would look like this one, which was the Navidad infection chain. And actually, it had a new version of it, an attack that happened in Brazil in 2020 Q4, and there were even some cases in the first quarter of this year. So there would be, again, some kind of a malvertising or a compromised website, or some social engineering, an attacker would send some links to a specific user. And if the user would be logged into his router, then first those scripts would try to guess the IP address of the routers. If for some reason there would not be an active session, then it would try to guess the credentials required for that specific router after identification. And since a lot of people uses default passwords, they might be able to just do that easily. Then with the CSRF attack or another one, actually they could change the DNS settings, the domain name server settings within the router, and that would result in quite a serious attack, because everyone who would join that same network, when they would try to access services known by them, they might be redirected to a phishing web server where actually the attackers could steal their credentials, and they could just redirect them to the original sites, so they might not even realize what happened. So you might ask, whether is that really simple, and why not? Because actually there is the same origin policy that was introduced in 95 by Netscape Navigator, which basically permits scripts to access data from another page only if they share the same origin. The purpose of this policy, obviously, is to prevent malicious scripts from accessing sensitive data from another web page. And it is worth mentioning that the same origin policy only applies to scripts and fonts. And writing data is still permitted in certain cases. And just to have an idea, our origin is, this should be visible, just a sec. Consists of the scheme, a host, and a port. But it also worth mentioning that there are some special cases like Internet Explorer, which doesn't consider the port as part of the origin, or if the site is within a trusted zone, then those sites can communicate between each other. So how can you relax the same origin policy? There is the first of the options is the cross-document messaging. This is not that widely used. The main idea in this case is that the receivers need to set up event listeners for the message string. And normally, if you would use something like this, it would require on the client side, on the server side, on the receiver side actually, to check for the origin headers. There's also WebSockets. Again, the SOP is not applied to WebSockets, and it's worth mentioning again that the origin header, which is part of the forbidden headers list, which means that scripts cannot actually modify it or set it explicitly. The browser makes that implicit for every connection request. Again, this is something that usually people don't really care about or don't really know about. And even in this case, you would need to check or validate the origin against a whitelist before accepting a connection. Moving forward, there's also another historical way of, let's say, working around the SOP, which is JSON-P, JSON with padding. Since by default scripts are allowed to be loaded from other domains, this could work, but it means that the server endpoint must accept a client callback parameter and return the data wrapped with that function. So for an example, if the client would make a request against the user's endpoint, he would need to provide a JavaScript function as a callback, and then the server would wrap the data and would send it back that way. So the JavaScript would be executed. Of course, this is not a really good idea from a security point of view, so make sure you don't use it. So the question is, are there anything else? Yes, of course. This is the cross-origin resource sharing, which allows restricted resources on a web page to be requested from another domain. Asynchronous JavaScript requests are forbidden to make course requests by default because of the same origin policy. And the browser and the server decides with the help of the course whether a request is safe to be served or not. For requests with possible side effects, the browser automatically sends a pre-flight, an option request, to check whether the real request should be allowed to be sent or not. So when it's considered to be safe, those are the simple requests, and the conditions for a simple request are that the HTTP verb must be one of those three, like get, head, and post. There shouldn't be any custom headers present. The content type of the request should be one of those three, like URL encoded, form data, or plain text. And if the request was made using an XML HTTP request without sending credentials, and no event listeners are registered to read the response. So basically, if an event listener is registered to read the response, or it is added by a JavaScript logic in the meantime, or to monitor the response or the upload, or a readable stream object is used, then this request will be blocked. Some browser will trigger a pre-flight check even if any of the permitted headers contain non-standard values. So for example, if you would say you would give a value for the content type, something else than, I don't know, maybe a random value. I believe this is how some of the browsers, for example, on iOS work. So what are the server-side headers that are required to actually enable course? So one of the most important is the access control allow origin, which basically configures which origins to receive requests from. These could be, and in many of the misconfigurations in the use cases, this is only can be used like a wildcard, which would accept all origins. There's then the access control allow credentials. This decides whether sending credentials are allowed. Like I said, session cookies, basic authentication, client certificates, and so on. What kind of headers are allowed, custom headers, in case of course requests, and what kind of headers will be sent back to the clients. There's also another one, access control allow methods, which decides which HTTP request type verbs the server accepts in case of a cross-origin request. It's important to mention that browsers now are requesting that if the credentials header is set to accept passed-in credentials, then you are not allowed to use the wildcard character in the origin, basically for security reasons. Now, some real-world examples of CSRF attacks, and yeah, basically the payloads of them. The first that you can see is against TP-Link routers, and it's basically a DNS change with CSRF via CSS import, which changes, in the example, the DNS name server to a certain malicious IP address, and the alternative DNS name server to Google's public DNS. So in case they would not be able to serve the request, then it will be resolved by Google. And the another one is something similar, but it's actually a post request using a form. And what it does is sets the remote management on a router to be accessible by the attacker, and it also overrides the HTTP password and some other parameters to be able to remotely access the router. So I was curious to see what public exploits are there currently. So doing a quick search on ExploitDB returned quite a few results, and actually looking into it just to see whether there were any payloads in the last 2 years. It seems that based on my query, there were around 123 exploits made public on the ExploitDB. So the question is how to prevent it, right? So let's see. The first and most recommended way of prevention usually is synchronizer tokens. This is actually what is implemented within the CSRFGuard. Another one is double submit cookie, which is again cryptographically strong random value, which is sent back as a cookie and a request parameter or a header. The advantage of it is that it's really easy to implement, and basically the server would just check whether the cookie value matches the header that has been sent along with the request. Moving forward, yeah, there are some defense in-depth mitigations like the same site cookie. This is actually the most promising from all of those. Another thing that you can do is to use custom request headers, which can also be configured within CSRFGuard, and checking the origin or referrer headers, because those are, again, as I said, the origin and actually the referrer header itself as well are part of the forbidden headers, so scripts cannot manually tamper with it. So it's, in many of the, or most of the cases, it's safe to check against. And yeah, one of the most, again, important things would be to follow the basic REST principles. For example, do not use GET methods for state changing operations. And yeah, one of the prerequisites of CSRF mitigation techniques is not to have cross-site scripting vulnerabilities within your application, because that way an attacker could defeat all the mitigation techniques. This could also depend, you know, if you can configure all the major attributes within CSRFGuard, then it will be slightly harder to do so, but still it can be done. So the same site attribute, that's basically a game changer, because it allows restricting the cookie context to first party or same site context. It can have the following three values. LAX, when cookies are not sent on normal cross-site requests, but are sent when navigation to the origin site happens. So this is rather for top-level navigation and only accept safe methods, which are get, head, options, and trace. There's a more strict version of it when the cookies will not be sent along with the request initiated by a third-party website. This practically means that if someone would send you a link, let's say on private message channel or so, if you would click on it, you would be redirected to the particular site that you might be logged in, but it will show you as if you were not. You would need to do a reload or refresh in your browser to be logged in. And the third option would be none. Well, that's basically how the internet worked for a lot of years right now. And that basically means that the cookies are being sent in all contexts. There's also a few new requirements with regards to this non-flag, is that it must be accompanied by the secure flag, otherwise the cookie will not be sent. If a server omits sending this attribute, some browsers will default to lax after 2 minutes when the cookie was created. And actually, this is something pretty new that was introduced in 2020, I believe, by the Chromium project. And since then, other browsers are starting to default to that as well. So for example, right now, if you would be using Chrome, then this is the default that you would see in your browser. So when you would need CSRFGuard then? Well, there are a couple of use cases. One would be when you need to support users with older browsers, for example, Internet Explorer, which still has like 1 year to live. And basically same site is not supported at all in Internet Explorers. Or if you have endpoints that enable state changing operations through GET methods, or you are using a framework, maybe even in legacy code or so. I've seen quite a few examples like this, where the framework permits HTTP verb interchangeability. So basically there, the logic is when you invoke a GET method, it automatically delegates to a POST. So basically they are interchangeable. And another use case is when you might need to disable the same site attribute is when you integrate with third-party services. For example, if you would use authentication via SAML and the identity provider is on another domain or so. It's also worth mentioning that currently Safari does not default to LAX nor Firefox before the version 69 and nor Firefox for Android before version 79. So you will still see a lot of users who might be vulnerable. So how does the application works? So if you are using an HTML or a JavaScript front end, first the HTML needs to load or refer to the JavaScript script, which is by default under the JavaScript servlet endpoint. This servlet would return the JavaScript logic together with a master token. If you have token per page enabled, then it would send another request to the same servlet together with the master token itself to query the page tokens. Again, if you have token pre-create enabled, because you might have a smaller application or so, the servlet will return a list of the list of all the endpoints within the application and their assigned CSRF tokens. Otherwise, it only returns pages that were accessed since the logical session creation. From this point on, all pages require a token to be sent along, either their dedicated token or the master token at the first use, after which a new page token will be created and sent back to the client. So moving on, if you configure to use single-use tokens, then after every usage, the token will be destroyed and a new one will be assigned through a response header. So you won't be able to use the previous token or reuse the previous token, better said. There's also a strict domain check option for the JavaScript endpoint that would not serve, if enabled, that would not serve the JavaScript logic itself and the CSRF tokens to requests that were made from another domain. Also, there's a referrer header check that you can enable that would also require a matching protocol, a matching domain, and there is an option to define a pattern, a regular expression that would actually act as a whitelist for the origins that are accepted. Besides that, there's also JSP taglib support, in which case tokens are injected on the server side, and you don't need to use the servlet for the JavaScript anymore. And actually, it would also give you an error of 400 if you are trying to do that. So what's new in CSRFGuard 4.x? First of all, it was heavily refactored, improved, and optimized. The modules were separated into distinct Maven modules dependencies. Right now, one of the biggest changes that has been introduced is that it now supports stateless web applications. So the tokens are not mapped to session IDs anymore. There is token per page support for AJAX requests, which did not happen before. The master and page token retrieval has been changed. A few race conditions have been fixed. We also have token injection into dynamically created content. So in case you have some fancy JavaScript logic that would create new elements in the page, CSRFGuard would automatically inject the relevant tokens to those elements in the DOM as well. A few other bugs that have been fixed, like do not inject tokens for unprotected or external links. This was quite important because an attacker could trick someone into clicking on an external link, and then they could save the assigned token to it. And also, there were some changes with regards to asynchronous AJAX request deprecation. The JS code has been changed to be parsable and minifiable, and so on and so forth. Actually, you can check the release notes on GitHub. So this is actually a screenshot of the test application that is also shipped, so to say, with CSRFGuard if you wanted to. So as you can see, on the right side, there is a log that would show the master token, the page tokens that were returned based on the master token. And as you can see, there are a few wildcards and regular expressions for different resources. And you can see in order how the logic injects the tokens to different DOM elements. Also at the end, there is an update of the form elements. And then another screenshot with the GSP tech support. I just wanted to show this one, that it doesn't do any requests in addition to the JSP itself. And even though the injection has already happened on the server side, this is really convenient and actually more secure. So yeah, basically that's the main flow that I wanted to show you. So I'm gonna just jump to some conclusion and recommendations. Yeah, so for developers, it is recommended to disable CORS or to configure very strict rules. For it, use the same site strict or lax. If required, to consider use 2 sets of cookies, one for general access and one for sensitive actions. I believe this is how Amazon does lately. Make strict assertions on the content type, require user input or confirmation or re-authentication or any kind of capture for critical functionalities. Do not accept GET HTTP methods for state-changing operations. Consider revoking access from users with old browsers based on the user agent, for example. Prevent cross-site scripting. Make sure that you have strict content security policies like script source and connect source, which would prevent loading scripts from other domains. And use anti-CSRF solutions like CSRFGuard if necessary. Besides that, non-default values slightly increase the complexity of the exploitation, so make sure that you don't go with the defaults. For penetration testers, bug bounty hunters, what you can do is to check for the same site cookie or attribute is flagged for is set for cookies. Check for permissive CORS rules. Set up your referrer policy to no referrer, because that way you might be able to bypass some of the validations. Send plain text content types, but pass JSON or XML content within and see whether that works. Reuse CSRF tokens between different sessions or remove the token itself altogether. Try to interchange HTTP methods. Try subdomain takeovers and start your attacks from there. Or you can try using social engineering to trick users into using an insecure browser. This page is only available on Internet Explorer or something like that. What you can also do is to automate your checks using Nuclei. It's an open source vulnerability scanning tool. This is what it returned for our default web application. Also, I've created a template, a YAML template that would detect different versions of CSRFGuard and whether it has token per page support or not. Also for people, recommendations for people surfing the internet, make sure to use modern and up-to-date web browsers. You can use Firefox container extensions to separate your browser sessions between the tabs, log out from sites that you, after you've finished using them, like internet banking or so. Consider using a separate browser or a browser profile for personal use. Do not use extensions that reduce the overall security posture of your browser, like disable CORS or enable CORS. And of course, do not download and execute files from unknown sources. Here you can see some references. I believe my time has just passed, so I won't have any time to show you some demos, but I'm gonna upload them maybe in a blog post to GitHub. Also, you can contact me on these following links, and of course you can ask me anything on Slack or Discord or other ways of